We have all been in this room before. A team is presenting results for the evals for an AI agent, trying to convey how well they expect it to perform in production. They show a metric, a percentage, sometimes color-coded to signal how happy we should be with it. And in this case, for example, they are telling us that the agent accuracy is 89%. So what is the presenter actually trying to communicate to us with this number? And how will other people in the room, your neighbors in this meeting, how will they interpret it? And what should the presenter be conveying instead if their goal is to communicate the real expectation of quality in production? When we run experiments and report on AI system quality, there is a lot to be mindful of. But the key enabler of quality in AI is having the right approach to eval. And the good eval is based on the organization having a shared foundation of language and concepts. We need to be able to define the problem we are solving, and we need to be able to communicate about it effectively. And human communication works so well because we each have a model in our mind of what the other person knows and understands. So without this shared context, without a grounded common set of concepts and terminology, we won't just find it hard to identify the question we want to answer and the problem we want to solve, but we will be in a situation where each listener in the meeting room will make their own implicit assumptions on what they are hearing, and these assumptions are likely to be wrong. So welcome to this course on Foundation for AI Evals and Experiment Design. My name is Fabio. I'm going to be the instructor for part of this course. And as you guessed, this lesson is focused on what I think is the most important part of the eval, which is having this shared language to express the uncertainty. And really, AI evals are about separating what we know about the system from what is still unknown and therefore uncertain. This lesson is really meant for everybody. So the idea is that everybody in an org can have this shared language and share knowledge so that communication can be made effectively and without, let's say, implicit assumptions that are potentially wrong. There is no background required, meaning that we are now going to see statistics, we are now going to see code, so everybody really should be able to follow this lesson. And I want to start by, dedicating it to late MIT professor Patrick Winston. He used to say very often that naming something gives you power and control over it. And I think, as we're going to see later in this course, giving the right name to AI eval, it's going to reframe a little bit the way in which we think about it. So there are three main reasons for why we study evals in AI. The first one is probably obvious. The eval, they have a foundational role. They help us decide whether we want to ship a feature or we want to hold it back. Also, if we have a fine-grained eval, we can understand which is the area, which is the aspect of the system we need to make better. And I think software engineers in most orgs are actually really good in optimizing the system once they know what they're solving for. The second reason for why we study eval in AI is that it is new and different than traditional software eval. So there are some practices, such as regression testing, that are well established in traditional software. And if we carry them on blindly to AI eval, we actually run the risk of having the opposite effect of what we want. And we're going to see what these practices are and why in eval we need to do something different. Sometimes we need to do the exact opposite of what we used to do. And the third reason is that we can actually use this AI development and the eval flywheel. So the idea is AI is now great, is a great teammate to help us develop, and the ability to quickly iterate on features and to quickly iterate on development also rests on the ability to run proper eval. So if the eval is quick and accurate, then we can easily and more rapidly iterate towards success. But it's really important that the eval measures the right things in the right way, otherwise this flywheel doesn't work. So throughout the lesson and throughout the course in general, we are going to use the example of a self-solve agent, a customer support request agent that essentially receives a customer support request and then accesses the databases, KB article, whatever info it needs to access, and then proposes a resolution to the user. We also assume that we have a way to magically assess the output of the agent. So we run the agent on a dataset, we obtain the output, and then we assume that we have some way of sending the input and the output to some judge. This can be a human judge or can be an AI judge, but for the moment we assume that we have this judge and that this judge is reliable. And we assume that this judge is gonna give us a rating for the agent. And for now, we just assume one metric. We assume that we get one, let's say, quality rating for the agent, which is on a scale of 1 to 5. And we consider ourselves to be happy if the rating is a 4 or a 5, and we're going to be sad if it's a 3, and we're going to be very miserable if it's a 2 or if it's a 1. So I promise that in this course we're going to talk about the language of uncertainty. So we do have to introduce some terminology, but this slide is the most terminology rich that you will get in this course, and hopefully will be simple to follow. So the first term we need to be familiar with is that of the experiment, and the experiment is a deliberate procedure which is carried out to generate and or to observe a result, an outcome. So for example, we roll a die and we look at the number, or we run our self-solve agent and we see the output that we get. The second term is that of the outcome. So the outcome is the result of an experiment. So we roll a die and we get a 4. We run the agent and we get a rating of 4 out of 5. The sample space is the set of all the possible outcomes. So if I'm rolling a die, the possible outcomes are 1, 2, 3, 4, 5, 6. I'm not considering in the sample space the outcome where the dice, lands on a corner or on the edge, right? I could, we just choose not to, right? And also for the agent, we choose to consider as a sample space, as a set of possible outcome, the rating 1, 2, 3, 4, 5, right? It may be that the agent fails or the judge fails and we don't get a result, or we get an error. And in this case, because of how we define the sample space, we discard those cases. So we only consider outcome as, for the agent, as a rating in a 1 to 5 scale. The final term in this slide, it's I find it a little bit awkward. I don't like very much the terminology, but that's what people use. And it's the event. An event is a subset of the sample space that we care about. So for example, you run the agent, and the event you care about, let's say, is whether you get a rating of 4 or 5, because those are the ones that, as we said, they make us happy. So the event is, I get a 4 or a 5. Or for a die, if you roll a die, you consider the event of, let's say, interest for you, maybe, as whether the number is odd or whether the number is even, right? Those would be event that you care about. So the event is basically only simply a subset of the sample space that's interesting for you for some reason. So let's see some examples so that we can firm these concepts into our mind. So one experiment could be I toss a coin twice. So that's the experiment. One experiment is I toss the coin twice and I observe whether I get heads or tail. So one outcome, for example, of the experiment is head, head. The sample space here is of 4 possible outcomes: head, 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 tail, tail, head, and tail, tail. Right? And the example of event I may care about is, for example, at least one head or all tails. Right? For our AI agent, I could say my experiment is I run the agent 6 times. Right? And I observe how many times I get a score of, for example, 4 or more. Right? So I observe how often we are happy with the outcome. Right? So an example of outcome is 3 out of the 6 times we get a score of 4 or more, and so we are happy. Right? The sample space here has 7 elements. So I could be happy 0 times. I always get a very low score. 1, 2, 3, up to 6 times. So all numbers from 0 to 6 are possible outcome of the experiment. Right? And as example of event, of a subset of the outcome of the sample space, I can say all answers are correct, so 7, or at least 4 are correct, so 4, 5, and 6 would be the correct outcome. Then I also added a more tricky kind of experiment, the Soccer World Cup for 2030. This is not something actually that we run, like somebody else runs it for us, so we may not have control over it, but we can observe who is the winner. So FIFA runs the experiment and we observe who's the winner. Example of outcome are any country that you like. And the sample space is currently there are 206 FIFA country that play the World Cup qualification. So we have 206 possible outcome, and as event of interest, this can be, I don't know, country from Africa wins the World Cup, or a country starting with the letter X wins the World Cup, which is something not very likely to happen. Some more examples to really firm the concepts in our mind. The experiment, again, we don't have control over it, but we can observe the outcome is it raining tomorrow, right? And in the first interpretation, we can say that what we care about as outcome is whether it rains or it doesn't. So it's a binary event. So the sample space has, 2 items, rain or no rain, right? And event of interest trivially are here, are either rain or no rain. We don't have much option for a subset of the sample space, right? Or I can be a little bit more fine-grained. I can say the experiment is still, I'm going to observe whether it rains tomorrow, but I care about how many inches or centimeters of rain we're going to get, right? So an example of outcome is we get 1 inch of rain. And the sample space, the possible outcome here is any non-negative real number. And the example of event are 0 rain, or rain for 1 inch or less, or rain for more than 2 inches, which sounds like a lot. But those are possible events. And the final example, I put a stock market, like you buy a stock at the price of $90 per share, then you see the price after 2 months, and you observe whether you made money or lost money. So an example of outcome is, hey, it's good, you gain $200, right? The sample space goes from minus $90, you lose all your money, to plus infinite if the stock goes, really high. I don't know if there is maximum. and events of interest can be, I don't know, we gain money, or we broke even, or we lost less than 10%. And so you can define essentially the event that makes sense for whatever you want to analyze. And with this, we come to what is probably the most important term in the language of uncertainty, and the most important concept, which is that of probability. So what is a probability? And I wanted to find some nice drum roll sound. Somehow I couldn't find it. So please imagine a drum roll in your head. So a probability, it's nothing but a number between 0 and 1, or a number between 0 and 100 if you prefer to count in 100%. And the key is it's a number to which we assign a meaning. And the way in which we assign a meaning is foundational to the language of uncertainty and to having this shared context and shared knowledge. Let me first start by discussing what is the thing we describe probability for. And the thing is, when we predicate about probability, we discuss about the probability of events. So for example, you roll 2 dice, that's the experiment, and what you may want to describe is the probability of getting a sum of 7. That's an event. It's a subset of the sample space, where the sample space is all the possible sums from a minimum of 2 to a maximum of 12. Or you may toss a coin 5 times, and you may want to discuss about the probability of getting all heads in these 5 coin tosses. Back to our self-solve customer support system, we may want to talk about the probability of getting a rating of 4 or 5 in the next run. And I also, as usual, put some events that are a little bit outside our sphere of control. The event can be who is the winner of the 2030 World Cup, and specifically, for example, the event I may care about is whether the cup is won by a team that never won before. That's the event I care about, and I want to define the probability for such event. And finally, I put something that I don't know if we could even call it an event or a result of an experiment, but the probability that the aliens exist, right? And I put this because it helps us to think about what is the meaning we want to assign to probability. So far, we haven't discussed about what's the meaning of this number between 0 and 1. What we are just saying in this slide is that we want to be able to associate probabilities to events, right? Before we discuss the meaning of probabilities, let me define 3 very simple rules that probability must follow. And these rules are basically what lets us connect the world of probability with mathematics, and lets us use math to reason about probability. And they're pretty simple. One is that the probability for any event must be non-negative. So event could be impossible, so they have a probability of 0, or can be possible, so they're going to have some non-zero probability, but they can never be negative. The probability of some outcome happening is 1. Right? So the probability of some outcome in the sample space happening is equal to 1. So if I roll a die, I must get one of the outcome of the sample space. Right? And the third one is that the probability of an event is 1 minus the complement, or the opposite of that. So if I say that I believe that there is a 30% chance of rain tomorrow, then there is a 70% chance of non-rain tomorrow. So with this background, we're finally ready to tackle our two main goals. One is to understand how we can ascribe meaning to probabilities and how we can estimate or compute such probabilities. So let's start from point one and let's see how we can ascribe a meaning to probabilities. So the first way in which we can assign meaning to probability is what is called the frequentist interpretation. So take the example of rolling two dice and saying that, the probability that the sum is equal 7, we say is 1/6 or 0.166. And we define this in terms of frequency. So we say if we were to roll these two dice infinite times, then the proportion of the times in which we will get a sum that is equal to 7 is 1/6. And that is our belief, and is based on this infinite repetition of the experiment. So basically we have an event A we care about, and we want to define the probability of A. And we say that the probability of A is the proportion of times that we run the experiment, and we get A as a result. So the result is compatible with event A. Or N of A is essentially the number of times that event A occurs in N trials. And we want to see how this number behaves as N goes to infinite, right? And that's our definition of probability. If we were to repeat the experiment infinite times, we would get a certain proportion, and that proportion, that frequency of events is the meaning we ascribe to our probability. So the probability is a frequency. So the frequentist approach has been common for many years, but it's really quite, I would say, unsatisfactory. First of all, we don't really have infinite experiments, so we never have the luxury to do that. And in fact, sometimes we have only one experiment, so there is only one 2030 World Cup. So it kind of doesn't even make sense to have a frequentist definition of the probability. We maybe could if we imagine infinite parallel universes in which we play the 2030 World Cup, but that would be, quite a stretch. And we want the meaning to be useful. There is no point in associating a meaning that, doesn't make sense for us. And, sometimes we have no experiment at all, like the probability of that the aliens exist. Sometimes, we just believe it. Yes, maybe we can study, we can get some hints that they exist. If we don't see hints, we don't know if we are not looking well enough or if they don't exist, right? So very often we don't have the luxury of having this frequentist interpretation. And I would argue that it's also not a very useful interpretation. Instead, what is more interesting is to think about probabilities as subjective belief. They do not describe uncertainty in the world, but they describe our uncertainty about the world. So they describe the fact that there is something about the world that we do not know. So for example, we could say the probability that aliens exist, I think it's 20%. I actually think it's higher, but I don't know why I put 20% in the slide, right? But that reflects your belief. Now, the aliens either exist or they don't exist. So there is no frequentist approach. There is no experiment. They either exist or they don't exist. But I don't know. So that's how I express my uncertainty and how sure I am that the aliens actually exist, right? And you can claim the same for, raining this weekend. I say, okay, there is a 30% chance that it's going to rain this weekend. That reflects my uncertainty. if you are a super meteorological guru and have all the data, maybe for you it's either 0 or 100. Maybe you are sure of the raining outcome this weekend. I am not, so my belief is 30%, right? And the same you could say for dice. I could say, for example, I've seen my friend roll these dice. I believe that these dice are tricked, and they tend to almost always give a sum of 7. So I express my belief that if my friend is rolling those dice again, I am 99% sure that the sum will be 7. Let me give you some examples so we can get a better sense for what we're talking about. And let me actually discuss some interesting type of beliefs that we can be talking about. So, for example, we can express a belief on whether an event will happen in the next run. So, for example, I can say I am 70% sure that it will rain tomorrow, or we are 80% confident that our agent will be correct on the next run, or I am 20% confident that, if we draw the next card, we'll do poker, right? And the things written in blue here, they are events. Either they happen or they do not happen. So there is no probability there. They either happen or they don't happen, right? The things in orange are our belief that express how sure we are that that specific event will actually happen. And notice that we are not saying like there is a 75% probability. It's all expressed in a subjective term. Is it I or we or our org? So the belief is held by a person or a group or an institution. It's not just there, let's say. And this is kind of in contrast with the frequentist interpretation, where we ascribe the probability to be a property of the system. Here instead we are discussing about probability as a property of what we know and what we believe to be true. The other kind of thing that we can express a belief on, and this is a little bit tricky, so I want to be a little bit careful here, is a belief on a proportion. So let's assume that we run our agent, I don't know, 10 times, 100 times, whatever, right? A belief that we could express is I am 70% sure that our agent will get the answer correct at least 80% of the time. Right? Or, for example, I could say I am 90% confident that at most 10% of the ratings will be low rating, 1 or 2, right? So here the experiment is I run the agent, let's say 100 times, right? And the event I'm looking, and this is binary, either it happens or it doesn't happen. Either I get at least 80 correct answer or I don't. So the event happening or not happening is binary, right? So the 80% is not a probability, it's a proportion that describe my threshold. Say, I care about situations where at least 80 out of these 100 runs are good. And what I'm saying, the probability is the orange part. I'm saying I am 70% sure that if I run the agent 100 times, at least 80 or more, more than 80 will be correct. Right? So the orange part is our probability. The fact that you see a percentage in the blue part, that is the event, and the 80% or the 10% for the second example are just thresholds that help us to define the event. But that's the event. The event either happen or it doesn't happen. While the probability, it's what defines how sure we are that the event will or will not take place, right? So it's very easy to get to get confused, but remember the probability here is our belief, and the proportion are just used to describe the event we care about. The third kind of things in which we often want to express a belief is on a statistics. So we have our customer support agent. We know that it's going to be rated into these 1 to 5 ratings. So we run the agent, I don't know, 10 times, 100 times, whatever, right? And what we want to predicate now is about the average or the median. So the event we care about is we run the agent 100 times, and the event we care is the mean between 3.8 and 4.6? Is the mean rating between these two values? Or is the median above 4? Right? This could be two events that we care about. And again, the orange part is where we express our belief. We can say to our boss, hey, I am 95% sure that if we ship this agent and we run it for n times, we are going to find that the mean rating is going to be pretty high, between 3.8 and 4.6. Or we're going to find that the median is above 4. And so we can be pretty happy, and because we are very sure that these two interesting events will happen. So in summary, probabilities as subjective beliefs give us a language to talk about how certain or how uncertain we are about specific events we actually care about. Consider in comparison how dissatisfactory this is. If somebody comes and say, I expect the accuracy of my system to be 89%, that statement means nothing, right? So we know for a fact with 100% probability that accuracy in the long run is never going to be exactly 89%, right? So fine, maybe the presenter mean the accuracy is in some range close to 89%, maybe, I don't know, 88 to 90, right? And first of all, if that's the case, then it's important to provide this range. If we don't provide this range, if we don't know what this range is, we are really not providing any information to the viewer. But the second thing is we should not just say a range. Saying a range per se doesn't mean anything. We also need to say how sure we are that the accuracy is going to be in that range. And we're never going to be 100% sure, right? So we need to say how sure we are, and we need to say the range, right? So again, sorry if the statement appears strong. The statement, I expect an accuracy of 89%, it doesn't provide any estimation information of any sort. It is, you should consider it as a completely meaningless information, right? It can only be used as a report of the past. So if you are reporting that, I don't know, you got an accuracy in the past of 89.27%, maybe that's interesting, and maybe that can help you to understand how to charge your customer for the quality of the agent, right? But it's not giving you any information in terms of estimate, right? So if we are describing our belief about the system, and if we are trying to estimate and to describe how we believe our system is going to behave in production, then the statement we need to make is almost always on this form. So we are X% confident, we are, I don't know, 90% confident that the mean rating is going to be between 4 and 5, right? So this is one example of meaningful statement that we can make, right? And when you say you are 90% sure, ideally that means that you are often right. So if you make 100 statement of this kind, where you say that you are 90% sure of something, what is supposed to happen is that 90 of these statements you're going to be correct, and on 10 of them you're going to be wrong. So it's not 100%. You are staking your claim that you are 90% confident, and this means that hopefully if your compass, your intuition is correct, you're going to be right 9 out of 10 times. 9 out of 10 such predictions are going to be correct. Let me express the same concept using words from people I highly respect. And one such person is, once again, MIT professor, Walter Lippmann. And he's talking about experiment in physics, and he says that any measurement without knowledge of the uncertainty is meaningless. And the same is true for our AI experiment. We get experiments, we get results, and these results are subject to uncertainty, right? And if we don't know, if we don't have a sense for the uncertainty, then our measure is meaningless. And he doesn't say this at a random point in the course. He says this in the first course and the first lesson of physics at MIT. And he says this to MIT students who probably, are kind of somewhat familiar with the subject already. So I think for people who are not familiar with the subject, I think it helps to reinforce the concept. And for some reason, he goes on and say, this is so important that you should hear this at 3 a.m. at night when you wake up. I don't know why he thought that his student would wake up at 3 a.m., but that's what he said. And I just want to be clear here. Sometimes I see engineering org that go with this 89% accuracy, and they're aware that it's imperfect, but it's a crawl, walk, run. There is almost some kind of engineering pride in doing things, in approximating things. But as I said, in this case, that approximation doesn't make sense. If you don't provide an estimate and the range, it means you really don't have any message to say, right? If you have learned something and if you have an estimate, then you should be able to say it in that form by expressing your belief and your confidence on that belief. If you cannot do that, then it means that you have no information to transmit, right? And the second quote that I really love is from Chris Peach. I highly, highly, highly suggest to watch his lecture video for CS 109. They are on YouTube, easy to find. And he says, those who are able to represent what they do not know make better decisions. And I think this is very true for us as well. As an org, we should be able to represent what we do not know. So with this, we move into the second part of this lesson, and maybe this is a good time to take a break. We've seen probabilities, we have seen what they mean. We still need to do a very important part, which is the estimation of this probability. And to do this, we'll introduce the concept of random variables. So I hope to see you in part 2 of this lesson where we're going to introduce the notion of random variables, and this will help us to, in turn, learn something about how we estimate these beliefs that we have been talking about.